So let's talk some more Lagrange error bound. Seems to be everybody's favorite error bound to calculate. Read the sarcasm in there. But it's really pretty straightforward, especially on the AP exam. They tend to have the examples fairly straightforward. So let's just go back through a little bit and remember what's going on here with this. First of all, we have to think in terms of the Taylor series for the function f. So this is what the Taylor series looks like. I've left a little bit blank at the end here because I want to make sure that we highlight what's going on here specifically for the remainder for the error bound here. So, of course, it's f of a divided by 0 factorial is our constant term, which is just f of a, plus f prime of a over 1 factorial times x minus a, plus f double prime of a over 2 factorial times the quantity x minus a squared, and so forth until we get to the nth derivative of f at a divided by n factorial times the quantity x minus a to the nth power. Now normally at this point it's just a plus dot dot dot, or rewrite this in terms of its summation notation, but I want to write out one more term because it's the structure of this one more term that's going to help us remember what the structure of the Lagrange error bound is. And so the next term, if we're just to follow the pattern, would of course be the n plus first derivative of f at a divided by n plus 1 factorial, and then all of that times the quantity x minus a to the n plus first power. And of course that series would continue on like that forever. So remember, in any Taylor polynomial, which is not the infinite series, it's a finite number of terms from the series, it's a partial sum, if you will, we have, what we're saying here is, let's look at the next term, and the structure of the next term will guide us in the structure for the Lagrange error bound. So we know that the Taylor polynomial will give us an approximation to the function, where this Taylor series will give us the exact value within the interval of convergence, of course. And so to estimate how good our approximation is for the Taylor polynomial, we need some method for doing so. Now, if the Taylor series happens to be an alternating series, then we could use the alternating series estimation theorem in place of the Lagrange error bound. It's when we don't have an alternating series that we have to resort to something else. So going to the error bound from Taylor's inequality, or the Lagrange error bound, the structure we get is this. We have m, which, as is stated down here, is an upper bound for the magnitude of the n plus first derivative. So it's m divided by n plus 1 factorial times the magnitude of x minus a raised to the n plus first power. So the structure of this term is just like the structure of the next term, or the first term left out of the Taylor polynomial approximation. So the Taylor polynomial stops at some term. The structure of the remainder looks similar in structure as to the term that was left off. But there are some differences. One, we have here in that next term, it's actually the n plus first derivative of f evaluated at a, where in the remainder we have that value is being replaced by m, where m is the largest magnitude taken on by this n plus first derivative, or at least some upper bound for the magnitudes. So although if we knew that value exactly, the n plus first derivative at a forever for all the next derivatives, obviously we wouldn't, maybe not obviously, but we wouldn't need to have an error bound. Or if that was easy to compute, we wouldn't have to have an error bound. We could calculate the actual value of the sum of the series. But in practice, that's not easy to do, so we need to be able to estimate what's happening, and that's where we're using this upper bound for the magnitudes of the n plus first derivative. The other difference is this quantity x minus a, which in our formula here that you see on the screen has parentheses around x minus a as opposed to absolute value symbols. We want to know the magnitude, or rather the largest magnitude of the distance our input is from the center. Remember, a is the center, So x is the input that we're plugging into the function in order to or to the polynomial to generate the approximation for the function. And so we're looking to see how far away from the center we can be. That's what this x minus a is. If we're trying to get a general bound, meaning on some interval, then we take the farthest point on that interval that we're going to be and use that as our input for x. And then if we're going to use a specific value, then that specific value is what we plug in for x. And then we just want its magnitude. We don't care about whether the sign is positive or negative because we're looking at just a raw magnitude of distance. So we're looking at the error as a magnitude, not as a signed value. So hopefully the structure makes sense. What we need to do every time we're doing the Lagrange error bound is we need to identify what degree polynomial we're using, and then we're going to go to the n plus first term because, or we're going to think in terms of n plus 1 because we need n plus 1 here and we need n plus 1 here. And then we need to get the n plus first derivative and bound the magnitudes of the n plus first derivatives on this interval and use that bound for m. And then see how far we are from the center, the maximum distance we are from the center. That's the quantity we're going to put in here. And we'll be able to calculate our error bound. So let's see how we can do this. Found an example on the internet which has us build a Taylor polynomial, as it says here. You can use your calculator. The function f has derivatives of all orders for all real numbers x. Assume that f of 2 equals 6, f prime of 2 is 4, f double prime of 2 is negative 7, and f triple prime of 2 is 8. Write a third degree Taylor polynomial for f about x equals 2 and use it to approximate f of 2.3, give 3 decimal places. The fourth derivative of f satisfies, that's part A, and we'll do that in a minute. The fourth derivative of f satisfies an inequality that the magnitude of the fourth derivative of f is bounded by 9 for all x in the closed interval 2 to 2.3. Now we want to use the Lagrange error bound to on the approximation f of 2.3 found in part A to find an interval AB such that A is less than or equal to f of 2.3, which is less than or equal to B, and we want to give that to 3 decimal places. So we'll get to that part in just a moment. Part A should be fairly straightforward, and you should be able to write that Taylor polynomial, that third degree Taylor polynomial. So pause the video and go work that out. So hopefully you were able to work that out. I'm not sure if I can squeeze it here on the screen, but I'm going to try. So what we have is, we have our function f of x is approximated by, well, we need the constant term is going to be 6 divided by, it's going to be our f of 2, which is 6, divided by 0 factorial, which I'm not going to write in the interest of space. So we're going to have 6. And then it's going to be plus f prime of 2, which is 4, over 1 factorial. I don't know why I'm writing that, but I, for some reason, am. Times x minus 2 to the first power. And then plus, we're going to take the second derivative, which is negative 7, and divide it by 2 factorial. And then, excuse my raspy voice here, x minus 2 to the second power. And then one more term, because we want the third degree, so we're going to have plus 8 divided by 3 factorial times x minus 2 cubed. No plus dot 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 here, because this is an approximation, as it says, and we are using a finite number of terms, so we don't keep going. We stop at the third degree Taylor polynomial. So that takes care of the first part of the question. The only other part of the question that we have to address now would be the approximation part. In other words, we have to use this to approximate f of 2.3. So to approximate f of 2.3, we just need to substitute in place of x the value 2.3. So this is going to be approximately 6 plus 4 times, I'm just going to do the subtraction here in the interest of space. 2.3 minus 2 is just going to be 0.3. And then plus, actually let's get rid of that. It's going to be minus because we see that minus 7 over 2, 2 factorial is 2, times 0.3 quantity squared. And then plus 8 divided by 3 factorial is 6. And then we'll have 0.3 quantity cubed. And then we need to generate an approximation for this. Actually, on the AP exam, you don't really need to approximate, get this. You can leave it just like that and get full credit. Actually, that's not true. I'm going to stand corrected because the problem does say to give the answer to 3 decimal places. So if it says to give 3 decimal places, we need to do that. But if they don't say that, then we can just leave it unsimplified, and they would have to work out or see that we did it correctly. But now we have to do that. I'm going to pause the video and come back with an answer. Well, it said calculator permitted, so I went and found a calculator really quickly. And if I ran this through the calculator correctly, and you did, we should get the same answer of about 6.921, which, as it says, to 3 decimal places. So now on to part B. It says the fourth derivative of f satisfies the inequality such that the magnitude of the fourth derivative of f is less than or equal to 9 for all x in this closed interval. So now we're going to use the Lagrange error bound on the approximation f of 1.3 to find some interval such that f of 2.3 is within that interval to 3 decimal places. Okay. The question like this, well, I haven't seen it asked like this on the AP exam, but I want to focus on generating the Lagrange error bound, and then we'll do a little bit of interpretation to get the interval that's being asked for here. Okay, so I'm going to get a clean sheet here. So what do we know? We know that the magnitude, now we're using a third degree Taylor polynomial, so this is the magnitude of r sub 3, which is going to be less than or equal to m over 4 factorial, 3 plus 1, times the absolute value of x minus 2 raised to the 4th power. So the only things we need to identify now are m and x. Now m bounds the n plus first derivative. Well, since we're using the third degree Taylor polynomial, we would need to look at the 4th derivative, so m is a bound for the 4th derivative. But they told us what the 4th derivative is bounded by. They told us back over here that it's bounded by 9. So that means we're going to have the bound for the magnitude of, or the error, the magnitude of the error of the third degree Taylor polynomial is less than or equal to 9 over 4 factorial times, well, what am I going to put in for x? Well, again, we're on the interval from 2 to 2.3, and we're using the value of 2.3. In other words, how far away from the center we're going to be. We're going to be, the center is 2, we're going to be at 2.3, so we got to plug in 2.3 for x, or note that we're going to be 0.3 units away from the center. So this is what that term looks like. So our magnitude of the error in the third degree Taylor polynomial is bounded by this value here, 9 over 4 factorial. 4 factorial is 24. So we got 9 over 24. And then we got this, 0.3. I can get rid of the absolute value symbol because it's positive, 0.3 to the 4th. And then I am going to go run that through a calculator again just to make sure I don't make any little, silly little errors. So I'm going to pause. I'll be right back. So running that through the calculator, I get this value here. So that the error in the third degree Taylor polynomial, its magnitude is bounded by this value here. So that's, to me, for the AP exam, the most important thing that we're working on. But let's go back to that last part of that question and make sure we know what's going on. So it says, use the Lagrange error bound on the approximation f of 2.3 found in part A to find an interval AB such that A is less than or equal to f of 2.3, which is less than or equal to B, and give the answer to 3 decimal places. Well, that goes from interpreting what's going on inside of this absolute value symbol over here. That's over here. Remember that this error, S sub 3, is actually, R sub 3, is S minus S sub 3, the third degree Taylor polynomial. And so what we have is our magnitude of R sub 3 is really the magnitude of S minus S sub 3, which now we know has to be less than 0.003037.5. I guess I don't need to use that many pieces of it. So what happens if I want to drop the absolute value symbol here? Not to go into the Algebra 2 details too much, we should recall that if we drop the absolute value symbols, then this quantity needs to be trapped between less than this positive value but greater than its negative. So that if I have negative 0.0030375, that's going to be less than or equal to s minus s sub 3, which will be less than or equal to 0.0030375. And remember, it wanted f of 2.3, and I guess I've been a little bit cryptic with this. F of 2.3 would be the actual sum. This right here is what f of 2.3 is. And our approximation is what we had over with the with this term right here. This is our approximation, okay? That's what we were about. Sorry, my battery went low, so it cut off. I hope it didn't cut off too much. But the s of 3 is our approximation. And so what do we need to do? We're trying to get f of 2.3 bounded between two values. So I just need to add s sub 3 to everything and rewrite this inequality. So I'm going to have s sub 3 minus 0.00300375 less than or equal to f of 2.3, which will be less than or equal to s of 3 plus 0.00300375. That looks like an 8. Sorry. Now, I'm not going to go do the calculation here just in the interest of time, but we did calculate s of 3. That value we got way back on the earlier screen. That was at 6.921, I think, if my mind is recalling it properly. I should go back and check. 6.921. So we can put in 6.921 into both of those. Wow, bad. 921. And if we plug both of those in there and do a little subtraction and addition, then we get the values of A and B asked for in the problem. So here's a slightly different version of a similar question. Estimate the error in the third degree Maclaurin polynomial for f of x equals e to the x on the interval from negative 0.4 to 0.2. Now the first thing to note about this is we aren't estimating the value of the or the magnitude of the area for this function evaluated at a particular value of x. Whatever I give for my error bound has to be true for all values of x given in the interval here in the problem. So whatever I say has to be true for all those values. The error bound that I give has to be true. And so what I have to do is think about the worst case scenario. This is similar to the idea that when we were using a tangent line to approximate the outputs of a function, the further the point that we were plugging into the tangent line to generate our approximation, the further that point was from the point of tangency, generally speaking, the worse the approximation was. And the closer the value was to the point of tangency, the better the approximation was. So analogously here, I need to take into account as far away from the center I am going to be and give my error bound based on that farthest distance, because again, generally speaking, that will give me the worst approximation. So I got to take that into account when I work this out. So it's not like the last example where we were computing this approximation at a particular value, f of 2.3. Now we're doing this on some interval, and I got to use the worst possibility so that when I give my error bound, it's going to be valid for all values within the interval. Now, I'm not sure if the AP examiners would ever give a non-symmetric interval around the center for this negative 0.4 to positive 0.2, but I really don't care because I want to illustrate a point in working this out. Okay, so we're going to hopefully this will clarify some of the issues that we have. Well, first of all, we're going to need an approximation, or rather a third degree Taylor polynomial, right? Third degree Maclaurin polynomial. And let me get a little darker pen here. So e to the x with a third degree is going to be, we'll have 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That's our third degree Maclaurin polynomial for e to the x. Something you should know. You should memorize and not have to generate by definition or other relationships. It's a basic one, fundamental. So know that one, memorize it. All right, so I'm trying to, again, get a bound for the error in the third degree polynomial. So I'm trying to bound r sub 3, its magnitude here. So, going back to our structure, I'm going to need an m, which we'll work out here in a little bit, and that's going to be divided by 4 factorial. And then since we are centered at 0, it's a Maclaurin polynomial, my center is 0, so x minus 0 is just x. So I can write it like the absolute value of x raised to the 4th power. All right, so now how do I find m? Well, I need to bound the n plus first derivative, so I need the 4th derivative of e to the x. Well, fortunately, the 4th derivative of the x is the same as all the other derivatives of e to the x. They are all themselves, okay? So I need to bound the magnitude of this function here. Now, we could go back and use our calculus skills from, A, B, and I'm trying to maximize this and minimize this, and then look at the magnitudes of those two values, the max and the min, and the one with the larger magnitude would be the upper bound that I would use for this. But I don't have to go through all the A-B techniques where I take the derivative and set it equal to 0, and so if I can find the critical numbers or find out where the derivative is undefined, and then test the endpoints, because we know how e to the x behaves. E to the x, is just our basic fundamental exponential that is always increasing, hits at 0, 1, and so we know that if we're looking on our interval from negative 0.4 to 0.2, we know where the maximum magnitude is going to be. The function is always positive and always increasing, so it has to occur at the right-hand endpoint. So my upper bound for this function here is going to be e to the 0.2. Problem with that is, how do you calculate e to the 0.2? We'll have a calculator active for this one here, but we're trying to do this in principle so we understand where the values are coming from. So I'm going to let m be e to the 0.2. Technically speaking, m is can be any number that's bigger than e to the 0.2. Now, e to the 0.2 is just slightly to the right of 0. If 0.2 is right here, then we know that we're going to have something bigger than 1, because e to the 0 is 1. If I plug in 1 for my input, then I get e, which is 2.7. So it's got to be somewhere between 1 and 2.7. 2 would probably work. I don't know, though. What would we have to... We'd have to raise this to the natural log of 2. And the natural log of 2 is not something I know off the top of my head. Or do I? I think it's actually about 0.7. So we could actually probably use m to be equal to the natural log of 2. Yeah, why don't we can let m equal the natural log of 2. Anyways, let's just use the 0.2. I'm sorry, I'm getting sidetracked here by my own work. The other thing we need to worry about is what do we do for this quantity in here? Well, again, we want to be the maximum distance from the center that's possible within the values we're trying to approximate. What's the maximum distance we could be? Well, on the right-hand side, I could be 0.2 units away. And on the left side, I could be 0.4 units away. So what do I want to put in there? Being 0.4 units away is further. So I'm going to put in 0.4 in for that quantity there, and that's going to be able to give me my approximation. So we're going to have our error, magnitude of the error in the third degree Taylor polynomial will be e to the 0.2 or some other nice number that you could find. Sorry, that's so sloppy. Let's see. I'm having a little trouble with the screen on this. There we go. Over 4 factorial. And then we're going to have our 0.4 to the 4th power. And then you can just work that out. But that would be our error bound that would work for all values within this interval, negative 0.4 to 0.2. I get as far away from the center as I can be. That's what goes in, that's what the whole quantity is in the absolute value symbols here. And then this quantity up here is something that I know is going to be bigger than every single value. Trying to get something not unreasonably large. I know 1,000,000 would be bigger, but if I put 1,000,000 in there for that value, then my error bound isn't going to be very good. So I want something that's reasonably close to the maximum value. So there's other values we could use, stuff that would avoid us having to calculate anything with a calculator. But that's not the point of this exercise. The point of this exercise is to know where these values came from. I found an upper bound, a maximum magnitude for the fourth derivative. That's what goes up there, or something a little bit bigger that's more convenient. And then over what goes in the absolute value symbols, how far, the maximum distance we are going to be from the center for any value that we may calculate in this approximation. I hope that clarifies some of the Lagrange error bound issues that you may have, and I hope you can take that and apply it to situations coming up in the AP exam or in other cases. Now go study.